Hey students, I thought I'd put together another little end of the chapter example problems that might help some of you. I was looking across here. These are the five I see. These are the five I would have liked to done if there was more time in class. So I thought I'd present them this way. And that way everybody, both online and in person, can see some extra examples being done. I printed the questions from the book here. And so here's the first one. It says, two identical loudspeakers, and they begin to show it down here, are driven by the same oscillator of frequency 200 hertz. The speaker are located on a vertical pole, a distance of 4 meters apart. So I'll just put in the little diagram, 4 meters. A man walks straight towards the lower speaker in a direction perpendicular to the pole as shown. And so here's the person walking, and I'm going to just kind of circle his head because that's ear level, and that's where he's going to pick up the sound. And he's directly level with the first speaker, meaning that the second speaker, the sound waves are going to come down at an angle. How many times will he hear a minimum of sound intensity? Well, this is a good time to talk about that constructive and destructive interference. Maybe a little mini lecture might be useful, but if we have a wave here and another wave, and we add them together, mathematically we say that the total wave is the sum of the two. And so if the crest of one lines up with the crest of the other, it gets really big. We call that constructive interference. But on the other hand, if the trough of the second one lines up with the crest, then they would tend to cancel each other because one number would be positive and one number would be negative. And so when they have two different waves, it's how they come together. And so if we think about these two speakers, maybe one here and the listener super far away, and of course I'll draw the listener right here. Maybe we'll put an O for observer and the two sources, source 1, source 2. But what's going to happen is this wave is going to travel along source number 1. Let me call that R1 for its length. And then it's going to travel along here. Let's call that R2. And of course, you can just see that R2 is going to be more than R1. And of course, how much more kind of depends where you are. If you are, say, here, because of the steeper angle, to me, that kind of looks like R2 is significantly more than R1. But as you get further away, they become closer and closer the same. Now, they never get exactly the same, but if they were, and so if you were really, really, really far away, you might say something like this. The delta R, the difference between the longer one and the shorter one, would be approximately 0. And that means if you had a bunch of waves here, the crest of one of them would line up with the crests of the other, and you would get constructive interference. But as you move in here closer, that begins to get off a little bit. And eventually it gets off enough so that the difference in their length is a half a wavelength. Now, maybe just to throw in another color here, I'm not sure where that would be. Let me just kind of roughly put it in my sketch right here. But I would say then what I'm looking at right here is that however many waves, let me just say there's 100 waves from the source to the observer, then up here there would be 100 and a half. So that the crest of one of them lines up with the trough of the other. Of course, they travel, so that keeps changing. At one moment, this is the crest and this is the trough, and the next moment they switch. But they're always, quote unquote, out of phase with each other. And because of that, they always cancel. And so there is where we'd call it destructive interference. Now, if you kept walking even closer, and so maybe I'll do this one in green, the difference between them gets even greater. Now, I will admit that that might be kind of hard to see because R2 and R1 are actually getting smaller and smaller. So both of these go smaller, but the difference between them keeps getting bigger. And then at some point, they may differ by a full wavelength. And so in green here, I'll kind of indicate that and say, okay, the length from source number 2 is one wavelength further than source number 1. And because of that, these two waves are going to match up crest to crest. And so when crest to crest line up, you get constructive interference. And so we like to, put this little phrase, maximum intensity. Maybe I should do that in blue here. Minimum intensity. And of course, this pattern could continue. So if delta R is a half wavelength, or 1.5 wavelengths, or 2.5 wavelengths, or 3.5 wavelengths, etc., etc., etc. Any integer and a half, then we're going to get our minimums. We're going to get destructive interference. But on the other hand, if this path difference is 1 wavelength, or 2 wavelengths, or 3 wavelengths, ... you're going to get your maximums, your constructive interference. Now, for this problem, I think they say here, how many times will you hear a minimum? Okay, so it's gonna be maybe somewhere, at least one, there'll be a half wavelength. Then as I get closer, the difference will be 3/2 of a wavelength. Then the difference will be 5/2 of a wavelength. And the most it can ever get, I know in my little description here, it makes it sound like it keeps going forever and ever. But if you look at this problem in terms of geometry, when the person walks and gets right up against this speaker right here, this distance here, R1, let me call it roughly 0. And this distance then is 4 meters. So the greatest the difference in their path length will ever be is 4 meters. We'll never get more than that. So at some point, this value is going to get greater than 4 meters, and that's why we won't get an infinite number of these. We'll just get, maybe 1 or 2 or 3 or 4. Not really sure how many. In fact, of course, that's the question. How many times will you hear a minimum in the sound intensity? Okay, so how many times? Well, why don't I do this? I can say that delta R maximum is going to be this 4 meters. Now, how many wavelengths is that? Well, maybe we better do a little calculation here for the wavelength. They told us to take the speed. It's kind of on the low side, but I'll take it. 330, or maybe it's really cold where they are. And divide it by a frequency of 200. And so 330 divided by 200 is 1.65. So call this page 1 for this problem. That means a half a wavelength. So divide by 2 would be 0.825. It means 1.5 wavelengths would be 2.475. 5/2 of a wavelength, so divide by 3 and multiply by 5, would be 4.125. And I'll stop there because that's over 4 meters. And so this says then that at some point along this path, there is a place where they differ by 1/2 a wavelength. And a little closer, they differ by 1.5 wavelengths, but never 2.5 or 3.5 or 4.5. And so the answer to A is just then twice. 2 times. Yep, that's all we're going to get. We're going to get when they are out of phase by 1/2 wavelength and out of phase by 1.5, but never 2.5. There's just not enough separation in this geometry to get that to work out for this particular problem. All right, and so I'm pretty sure that's why the author kind of gave this as a first one, to kind of force you to think about the fundamental physics of, why do you have this minimum in the first place? And then, of course, looking at the geometry, you will hopefully come up with the idea that the most you'll ever get is 4, and so the third minimum, if you will, is greater than that. And so that's not going to happen. All right, so there's 2. And, of course, then they go on to say, well, then how far is he from the pole at these moments? And in this case, now we can say these 2 moments. Okay, so I guess the first one would be when delta R is a wavelength over 2, which is 0.825. And then we'll talk about the second one here in a moment. But since this has to do with the path difference, we probably need to do some geometry here. Again, if this is source number 1 in my picture and source number 2, they are separated by 4 meters. And if we call this then, this R1, how far is this individual? This right here, R2, is then the hypotenuse of this right triangle. So this would be R1 squared plus 4 squared square root. And so if we put these 2 thoughts together, this geometry and then the physics of destructive interference, we would say right here, R2 minus R1. That is the square root of R1 squared plus 4 squared. Minus R1 is to equal 0.825. And so now we have an equation that has an R1 in it, and that's, I think, how they want us to answer it when they say how far, right? How far is he from the pole? And so that would be the R1. Now, sadly, this is a radical equation, so I need to do some, tougher mathematics. This would be R1 squared, and I'll just put 16, and I'll do 0.825 and add an R1. And then, of course, to get rid of the square root, I got to square both sides. So this would be like a plus b squared. And so that would be a squared plus 2ab plus b squared. And then, fortunately, there is an r squared showing up on both sides. So that when I continue with my mathematics, I can take this 0.825 and square it. So 0.681. And here, 2 times 0.825, 1.65 R1. And then I'll just get an R1 by taking the 16 and subtract that number. Enter. Then divide by the 1.65 and get a distance of about 9.28 meters. Now, I don't see a mistake I made, but I would have thought it was a little further than that. Maybe I'll just check. If that's the distance of R1, then let's look at R2. It would be that number squared plus the 4 squared, which is 16. Add it together, take its square root. Okay, that would be the distance. And then if I subtract off the R1, that should be my, half a wavelength. Okay, so there would be my first answer. A little over 9 meters away. And now my next answer is going to say that delta R is this 1.5 wavelengths that we calculated here. So this would be 2.475. And let's do that same logic. This would be the square root of R1 squared plus 16 minus R1. Bringing it to the other side, 2.472 plus R1. Then I'm going to square it, because then that will make R1 squared plus 16. And so in this case, I would have, again, an A plus B squared. So this would be the 2.475 squared. And so 6.16 plus 2 times 2.475. 4.95 R1, and then the B squared would be the R1 squared. And like before, the R1 squareds go away. And so we will get here 16 minus 6.16. Then divide by 4.95 and get a distance of very close to 2 meters. I'll call it 9. And that seems about right, although I will go ahead and check it here. If I take that number, I square it, I add to it a 16, I take the square root of all of that. That would be R2. And if I subtract the R1, that should be 1.5 wavelengths. And yep, sure enough, that's very close to what we listed for the 1.5 wavelengths. All right. Oh, good. And I think that was the whole problem. All right, nice. So, like I said, nice little interference pattern. Let's go on to the second example here. Okay, how about number 22? Number 22 says this. A violin string has a length of, I'll call it 35 centimeters, and it is tuned to a concert G, where the frequency of G is 392 hertz. Where must the violinist place her finger in order to play a concert A? And a concert A has a frequency of 440 hertz. Now, if this position, okay, so another question. Let me pause right there and say, all right, maybe a good review is in order here, because this discussion about waves on a string we said you could have something that looks like this pattern. The key recipe is if this is one end, say the bridge of the violin, and this is the neck here of the violin, those two are tightened up, clamped, locked into position, if you will. And so those can't move. I don't play the violin, and so I was thinking that some of you, like me, might benefit from a little picture here of what it looks like, and it has the wording here. I guess this is called a nut on the violin, and this is called the bridge on the other end. But the string then is pulled tight back here with the tuning pegs. And then you have it clamped here. And of course then tied off here. And as it's quote unquote clamped, there's a certain length to it. And the pattern could look like this, but there are other patterns if we kind of go through a little review. Another option is if you're clamped at both ends, it could have this type of pattern. And so we call these the standing waves. And if L is the length of the string between the 2 points that are clamped, then in this case you can see L is equal a half wavelength. In this case, L is 2 half wavelengths. And if I go ahead and draw one more picture that would fit the criteria where it's got to be a node on each end, which of course would put another node in between them. So this would have no nodes in between. This would have one node in between. This would have two nodes in between. But of course in this one you can see L is 3 half wavelengths. And so in general, L would equal to an integer number of half wavelengths. And so our logic being, if you go to calculate the frequency of this vibrating string, which is its velocity divided by its wavelength, and solving up here for its wavelength then would be twice L divided by this n being an integer, 1, 2, 3, 4, ... Then we can write this as V over 2L times N. And of course, then that's why we would have the different frequencies or the different harmonics. Taking this to be the fundamental one for our problem, we can set n equal to 1. And so we have an equation as V over 2L. And I suppose I could even say V coming from a string would be the square root of the tension divided by the mass per length. And so there's our violin. And in fact, as you know then, you can both tune and play the violin, or the guitar for that matter, because by putting your finger at different locations, you are essentially, where's the fingerboard? Yeah, right here. You'll be putting your finger at different locations, essentially making the two clamped ends shorter than it was when it went from the nut to the bridge. Now it's going from the bridge to your finger, wherever you touched down with your on the fingerboard. And so by lowering this length, you're going to raise the frequency, and that's why this problem. Whoops, pick that up. That's why this problem talks about the string you're going to use is the G string. It has this frequency if you don't put your finger on it. But as you put your finger on it, you can change the length of that string, and that's going to make the frequency go up, and that's why you're going to be able to play 440. Now, there's only so high it can go, and so you're going to have other strings for just that purpose, so that you can get a whole range. And the other strings are then tuned different, and that's what I would call these factors. They could be under different tensions, or they can have a different mass per length for each of those strings. And so, you would probably pre-concert go in there and kind of adjust the tension until the tension's, just right, so that this whole string makes, a sound of a G, okay? And, of course, they did not give me the tension or the mass density for this problem, but they did say it was tuned, the string was tuned to a G. So if we take that, we could say the frequency is 392, and the length of it is the 0.35 meters. And that'll give us this missing piece, which I'll call it the velocity of the waves on the string. Or maybe to say the same thing, it won't give us the tension individually or the mass per meter individually, but collectively, it'll give me the 2. And so grabbing my calculator, this is 392 times a 2 times a 0.35. And so this is 274.4, and then meters per second must be the speed of the waves on the string. By the way, not to be confused with the speed of the sound waves. Once that string starts vibrating, it's now going to push on the sound. And although it's not part of the problem, the box I'll make here has to do with the next effect, which is really the purpose of playing the violin, is to make that vibrating string then vibrate on air molecules. And if we take this to be, sound and air at room temperature, we could say then the velocity of the sound waves is 345. And again, what I want to emphasize then is that's why this speed here, for the speed of the waves on the string, is a different number than the speed of sound. And again, not that we had to even go this far, but the connection is that they would have the same frequency. So in other words, as a string goes back and forth, back and forth, back and forth, it's going to hit the air molecules back and forth, back and forth. And so these two different waves we're talking about, the waves on the string and the sound waves that are produced from the string hitting them, are going to have the same frequency. That's kind of the key. But they're going to have a different velocity, which means they're also going to have a different wavelength. And so if I go to calculate the wavelength of the sound waves, I would go 345 and divide it by 392, coming up with 0.88 for the wavelength. Whereas you can see here, if this is the length of the string, if you double it, you get 0.7. So on the string, the wavelength is 0.7 for the string. And so let me just say it again. Two different waves, same frequency, but different wavelengths and different velocities. And so you got to kind of be careful working with our stringed instruments, that you realize, okay, wait a minute, there's two sets of waves going on here. There's the waves on the string that are then generating the sound waves, and since they generate them, they're going to have the same frequency, but not same velocity and not same wavelength. Unless coincidental, but not likely. Now, maybe I better call this page 1. Actually, did I answer this? No, I haven't. I haven't answered this question quite yet. All I found out so far is the velocity of it. And I used the tuning of it, that it's a G, to get started. But now we're going to place our finger and try to get a new frequency. And so rewriting this equation as frequency equals 1 over 2L times the square root of tension over mass density, or maybe just call it velocity. When I try to play this musical note A, I want a frequency of 440. And so I've made the frequency higher, so I'm going to have to make the length of the string smaller. And like we mentioned, that means you're going to touch it somewhere around here on the fingerboard and make it smaller. Okay. And then this square root of t over mu is what we did right here. So this is a 274.4. And then, of course, you can see mathematically the unknown here is the length, which should be smaller than the 0.35. So let's see what we get. I'll put the numerator there, 274.4. I'll divide it by the 2. And then we also divide it by the 440 that I'm going to bring over, because when I bring the L to the other side, it's in the numerator. And so this is going to be 0.3, I'll call it 12 meters. And so that would be from the bridge to the place where you set your finger, maybe right there, not all the way back to the neck. Remember, the neck was 35. So 3.8 centimeters from really this nut. Okay, good. So that's the first half of this question is, okay, where do you place your finger? Now, the next part, it says, if this position is to remain correct to about half the width of your finger. All right, so I'll pause here. And again, I probably could do a better job if I had really played the violin. I don't. But what happens with any of your stringed instruments is the tension begins to come loose. And so to get the same frequency, come back here to this equation, if the tension gets less, usually because of the string itself, actually, just kind of stretches. But it's been under tension for so long, it just kind of, that becomes its new position. And so the tension actually just kind of fades away. So that means this goes down. So if this factor goes down, in order to keep the same frequency, your L has to go down. And so it may have been tuned right here when you touch that string, but as the concert goes along, or as the days, and assuming you don't retune it, go along, you're going to have to touch it, further out, because to get that same frequency, if this goes, I think I just said that backwards. This will go down. The L must go down. So I guess you're going to touch it closer in. You're going to go this way. And you don't want it to get, too extreme. You don't want to be touching it further in. Plus, what you really don't want to happen is when you don't touch it at all, if the tension drops, you're not going to get this nice G frequency. If you're trying to get the A and the tension's off, you can adjust that by where you touch the violin. So you can move that finger in. But that is kind of the idea here. And so if this right here is, where I would be touching the fingerboard, and that'd be the distance from the fingerboard to the bridge, then if I'm willing to, say, okay, I'm going to kind of move in a little bit to get that A, but too much just tells me it's out of tune. They're trying to say that you could move in, and so maybe I'll call this L1. This is what the kind of the original length. And then as the concert goes and the tension begins to change, you would say, okay, I need to put my finger a little closer in. And in this case, they're saying willing to take a, how far? 0.006 meters. Right there. About the width of your finger. So you know it's somewhere in there of your finger, and you start doing further down, you're like, okay, that's not right. I gotta tune it. And so if you're willing to, move your finger around to about the width of your finger, then you could, subtract off 0.006. And I guess 6 taken from 12 is 6. Is that what that rounds to? Yeah. So 0.306. So as you, like I said, begin to deal with the string stretching and lower tension, you're willing to move your finger into this far. And so it was here, and you're willing to move it in a little bit more than that. You're going to retune it. Okay. So knowing kind of what the question is asking, if this position is to remain correct to about half the width of your finger, what is the maximum allowing percentage change in the string tension? And so that's what we've been talking about, is that tension is going to go down, so your L has to go down so that you still get the 440. And of course, you can see it here when you do the calculation. Transferring this down here, I still want, after my tension has gone down, to still give me a frequency of 440. The length, though, I'm willing to go down to is that, minus half the width of the finger, 0.006. And then, of course, we can get the square root of tension over mu now. Let me call it tension number 2 as it went down, because what we did on the previous page then, we might say this is tension number 1. This is where tension we started at when we tuned it before the concert. And so now this new tension, T2, is going to be a little bit less. So trying to solve this, I'd go 440 times 2 times 0.306. And so this comes out to be 269.3 meters per second for the new velocity. And notice from page 1, it's smaller by a little bit. That smaller amount is because the tension went down. And so that'd be the new velocity, and that's not quite what they asked. What did they ask? Look at, here's a weird way to ask the question. What is the maximum allowable percentage change of the tension? So why don't we do this? We don't have exact numbers, but we could look at this ratio. Because that ratio really is what is T2 compared to what it started with. Okay. And so coming over, let's see. Well, maybe I'll just continue down this page 2. Remember velocity then, which is the square root of tension over mu, means that velocity squared times mu is the tension. So this T2 over T1 could be written as velocity number 2 times mu, velocity number 2 squared, as velocity number 1 squared mu. And the mass density isn't going to change. So that's good. I was getting a little nervous about that because that mass density kept showing up. And I was like, I don't know how that is going to be figured out. It's not given anywhere in this problem. So hopefully that went away. But as we just calculated, number 2 is 269.3. So I'll square it. And the original speed, when we tuned it in the start of the concert, was the 274.4, and we'll square it. So 269.3 squared divided by 274.4 squared hits an equal, and it's 0.96. And so I would say that the tension of number 2 has dropped down to 96% of its original value. So we lost 4%. And they say, what is the maximum allowed percentage change? So we're looking at 4%. So we're willing to say within 4% now. We'll have to move our finger so much that it's not a good idea. All right. Well, I guess like a lot of my videos, I hopefully added a lot of extra information that help you work through it and the logic. It did take extra time. So why don't I cut the video here and say, okay, here's the 2 examples, and they're each blue. It kind of makes sense why it took a while. And then I'll make another video for the other 3. And there's only one blue one, so maybe they'll go the same time since there's 3 of them. But I think they're a little bit easier. All right, take care.